Hello. Today we consider the second major type of question that requires calculus to be answered. And that question involves area under a curve. If I have a function f of x that is continuous on a closed interval a, b, where f of x is greater than or equal to 0 on that interval, in other words, a picture somewhat like what I drew, we can find the question that we want to know is, I want the area under f of x above the x-axis between x equal a and x equal b, the area outlined above. Now, to do this, we are going to have to use calculus, but at the moment we will kind of build up on how we can end up doing that. We can, using algebra, approximate this area. If I take and break this apart into rectangles, and let's suppose that I use an endpoint of my interval to, suppose I use the right-hand endpoint each time to get the height of the rectangle, we can then approximate the area under the curve by looking at the area of rectangles. That we do not need calculus for. And so today we want to look at area approximation using rectangles. And again, we have a curve that is non-negative and continuous. And in Calc 1, we will consider this in two different ways, using the left-hand endpoint of my subinterval, these little pieces here, to get my height, and using the right-hand endpoint. So we will label these as L sub n. This is left endpoints of the subintervals with n rectangles, and R sub n, which is using right endpoints and n rectangles. So the idea is we will take our interval from A to B and break it apart into n subintervals. And we will assume that all of our subintervals are equal width. It's just easier that way. And so I will label this as x0, x1, etc. We have a general interval in the middle, which is x sub I minus 1. This is always a little bit difficult to write. X sub I minus 1 to x sub I. And then this is x sub n on this side. So this interval here is blowing that up. X sub I minus 1 to x sub I. And if we want to use the left-hand endpoint, I'm always talking about x sub I minus 1. If I'm using the right-hand endpoints, it's x sub I. Okay? So, let me erase this for a moment. L sub n then becomes, using the left-hand endpoint, f of x 0 times delta x. Delta x is the width of the rectangle. I should have said over here, the width of the rectangle. We label delta x, and that becomes is just b minus a over n. I take the overall distance and divide it by n. That gives me the width of each rectangle. and they're all the same. So f of x 0 delta x, that's using the left-hand endpoint of the first subinterval to get my height, plus f of x of 1 delta x, that is the area of the second rectangle, using the height at x sub 1 to get my, the functional value at x sub 1 to get the height, etc. The general left-hand endpoint, f of x sub I minus 1 delta x, plus continue on until the very last one. If we end at x sub n being b, then the left-hand endpoint is x sub n minus 1. Now, this notation is kind of difficult to work with. And so we rewrite this, or we can write this in what's called summation notation by I equals 1 to n, f of x sub I minus 1 delta x. This is a loop. It's kind of, if you've done any kind of programming, this is kind of a loop that starts at when I equals 1 and we end at when I equals n, and you add in between. It is what we have up above. Similarly, r sub n would be the summation I equal 1 to n, f of x sub I delta x. In this case, I'm always using the right-hand endpoint as I move across. So let's look at a couple of examples. I'm going to erase some of this, but keep some of this. Erase that, just keep the condensed version so we can view it. And let's suppose that I want the area, I want to approximate the area under f of x is equal to x ln of x on the interval from 1 to 3. This function is always non-negative. It's 0 at 1, but it's always non-negative on this interval. And we're going to first do this with 4 rectangles and using right endpoints. Okay, so if I want to do this, the first thing I'll do is draw a number line here and break this apart into 4 subintervals. Next thing I need to do is get my delta x. Delta x is b minus a over n, or in this case, 1/2. And so that means that this value here is 3/2, this is 2, this is 5/2, and that's 3. Just add 1/2 each time. You can use decimals, it doesn't matter. I'm just doing fractions because it'll be simpler. I'm not going to get an overall value at the end. I'm going to leave that part of it. And then my approximation, L4, remember, L4 is an approximation for the actual area under the curve. It's not going to be the area, but it's an approximation. L4 would then be, following what I have over there, the functional value at, first off, let me label these. This is x0, x1, x2, x3, x4. So f of x0 would be, I take the number that's associated with x0, which is 1, input it into my function. This would be 1 times the natural log of 1, which is 0, times my delta x, which is 1/2. Plus, now I equals 2. The functional value at x1 is 3/2, so this becomes 3/2 the natural log of 3/2 times delta x, which is 1/2, plus my functional value at x2, which is 2. I get 2 natural log of 2 times 1/2. That's my delta x, plus at x sub 3, 5/2 natural log of 5/2 times 1/2. And at that point, I am not going to do this, but we can actually calculate this out, use a calculator, get an approximation, decimal approximation, and get a value, and we can get decimal value for that. Okay? Now, I want to use the same function, and I'll do this one in a different color. F of x is x ln of x. Again, same interval, but this time I want to use 6 rectangles. And I'm going to use the, this was using left endpoints. I don't want to. Let's use 6 rectangles doing right endpoints. I was not thinking about what I was doing. So, now I need to break this interval apart into 6 subintervals. Again, I will try and get them somewhat evenly spaced. My delta x in this case is, again, b minus a over n, or in this case, 1/3. And so my values become 4/3, 5/3, 2, 7/3, 8/3, 3, and R6 in this case is going to be, let's write our values, x0, x1, x2, x3, x4, x5, x6. Following my formula over there, f of x1, which is 4/3 natural log of 4/3, times my delta x, which is now 1/3, plus f of x2, 5/3 natural log of 5/3, times 1/3, plus 2 natural log of 2, times 1/3, hopefully I'll have enough room, plus 7/3 natural log of 7/3 times 1/3 plus, and I'm not going to have room, and that is 8/3 natural log of 8/3 times 1/3 plus 3 natural log of 3 times 1/3. And again, we can calculate this out and get a numerical value for it.